All right, so my name is Philip. I work at Akamai. I'm the principal RAM distiller. RAM stands for Real User Measurement. It's data, performance data we collect from users as they browse the web. It's JavaScript, sits in a web page, and it just measures how long it takes the page to load up, sends that back to our services, and I do the analysis on that data. So today I'm going to be talking to you about a module we wrote called CurlHTTP that is based on libcurl. It's a more Julia-like way of using libcurl in Julia, rather than using libcurl, which is more C-like. How do I take away this search box up there? That's better. So very quickly, if you wanted to get CurlHTTP, it's available in the package registry. It's called CurlHTTP package add. Current version is 0.1.3. And there are docs for pretty much the entire library. There's also tests, so it's very well tested. So first, we'll just go over a brief overview of how do you do HTTP in Julia. Right? There are various ways to do HTTP. Obviously, Julia has HTTP client built in. That's how you can download packages and install them. That's based on downloads.jl, which in turn is based on libcurl.jl. libcurl itself is a very low level. If you've ever written C code and used curl in libcurl in C, using libcurl.jl is almost identical to that. Your functions you'd write look a lot like C functions. The way you call it looks a lot like C. You'd pass in pointers and you'd get back pointers, and you have to deal with all of that in Julia, which is not very nice to do. There's also some functions which allocate memory inside the function, and then you have to figure out whether you need to free it or let libcurl free it. So it is not, if you're just trying to write an application in Julia, trying to work through all of those things is not the best use of your time. HTTP.jl is a higher level API. It's pretty good. It's got client and server modes. So libcurl itself is client only. HTTP.jl is both. It's kind of complicated to do mutual TLS. It's okay to do TLS. First, a show of hands, who knows what TLS is? All right, I'll cover it in a bit. But so it's kind of okay to do TLS. It's hard to do mutual TLS, and I'll talk about both of those. And also, it doesn't support parallel requests on a single thread. Right? If you wanted to do parallel requests in HTTP.jl, you have to spawn multiple Julia threads and do a download from each of them. Then there's, of course, downloads.jl, which is a very high level. You give it a URL, it downloads it. That's pretty much all it does. A few configurations you can pass in, but that's what it does. And so that leaves us to CurlHTTP, which we wrote because none of these three ways solved our use case. And I'm going to talk about that in the rest of this talk. So at a glance, there's two interfaces. Curl Easy, which is the simplest interface if you wanted to make a request a single URL, fetch that and save it. It's also what happens when you run curl on the command line. So if you did curl and some URL, it would just fetch that using HTTP GET. And then there's curl multi, which allows you to do multiple requests in parallel over multiple different connections to different servers or the same server, however you want to do that. We have the same API across both interfaces. So you don't, once you initialize your object as a curl easy or curl multi, you then no longer have to think about which one you're using. You can just call all the same methods, and we use multiple dispatch to figure out what to call. You can read or write data to and from and to HTTP servers as a block. So you send if you did a post, you can send the entire file as one chunk. Or if you're reading, you can read the entire file as one string. Or you can do it as a stream, in which case it'll read byte by byte and call your callback function whenever a certain number of bytes is available. And lastly, we support TLS client certificates as well as certificate authorities, which I'm going to talk about in a bit. What we don't have is WebSocket support. So many HTTP clients do have WebSocket support. CurlHTTP does not. It is a transactional model, so you get something back, and then you're done. Whereas with WebSockets, you'd keep the connection open for a long time and do multiple requests over that. And there's no cookie handling yet. You have to maintain your own cookie jar. Again, it's not that high level that it would do cookies just like downloads.jl does or HTTP.jl does, but it's not too hard to sort of maintain your own dictionary. So what was our use case is we have internally at Akamai, we have our application that needs to call out to several web services. We need to make get, put, post, and delete requests to these web services. Very importantly, it needs to be over HTTPS, so the server is, the connection is a secure connection. And also more importantly, it has to have mutual TLS, which means the server needs to know that the client is who they say they are. So we do not allow requests from anybody on the web. It has to be a certain host that's making the request, and we decide that by using a client certificate. We need to use a custom certificate authority because internally in Akamai, we'd have our own certificate authority that only signs things inside of Akamai, whereas outside of Akamai, you'd have a public certificate authority that all of your browsers know and can connect to. And we need to process the response data, which is JSON stream data. So essentially, JSON stream data is multiple JSON objects coming one line at a time. There's a new line character at the end of the JSON object, but it comes through in one full stream. So you need to be able to detect when that object ends and parse it at that point. And occasionally make multiple parallel requests and post-process them to combine the responses. So like we might request to 2 different REST APIs or same REST API, 2 different pages, and then combine a data frame later on in Julia using that API. So this is where I talk about TLS. For anyone not familiar with it, TLS stands for Transport Layer Security. If you're familiar with the OSI network model, there's various layers. There's the internet or the network layer, which is what your IP addresses are. There's a transport layer above that, which is sets up sessions between hosts. And there's the application layer above that, which is essentially your HTTP client or your browser. So transport layer security runs at the TCP, or the transport layer, which is within TCP at this point. What it does is uses asymmetric key cryptography. It's a little more complicated. So typically the server has its own key and its own certificate. It signs its certificate with the key. And then there's a certificate authority that also signs it. And the client, when it makes a connection to that server, it gets the certificate. It checks that the certificate is valid from the certificate authority. It checks that the host name matches the name within the certificate. So it knows that it is talking to the right server. And that's how it knows its connection is secure. And once that is done, then they exchange a symmetric key for the rest of the session. And the reason for that is asymmetric key cryptography is slow. Symmetric is fast. So you want the majority of your communication to be done over symmetric key, but you need to safely exchange that key, so you use asymmetric for that. Mutual TLS takes that a little step further. So the client also has its own certificate, and typically that certificate is signed by the server. So let's say we have a database server that's responding over REST, and whenever we have a client that needs to connect to that, that server will issue a certificate, or rather, we will create a certificate, create a certificate signing request, send it to the server. The server will sign it and send us back that signed certificate. So there's kind of a secure way of exchanging certificates without revealing your own private key. Right? And certificates contain a common name. So for example, my certificate on this box here, I have my own certificate that can connect to Akamai servers, and it's got a common name, which is essentially my name. So when I connect to the server, it'll see the common name, and it'll look up my permissions based on my common name. Right? So that's how mutual TLS works. It does not have to be within Akamai. We've done it. You'll find many places on the web that use it as well. Typically, places that give you certificates will use certificate-based authentication. So how do we do a simple GET request in CurlHTTP? Pretty straightforward. First, using CurlHTTP. Then we initialize the object. So curl easy, give it a URL, give it the method. Default method is get. And by default, verbose is false. You can set it to true to see more of what it's doing. So it'll print out all the messages that are being sent or received over the wire. And then you call curl execute. And it returns a tuple of 3 elements, the response, which is a curl specific message. the HTTP status code, which is whatever your HTTP server responds with, and then any error message. Now, once it's done that, it also stores all of the response data within this data buffer as a uint8 vector, right? And you can get the response body by just converting that to a string. And response headers are also stored in response headers as a vector of strings. So this is the simplest way of calling it. It's synchronous. You make a request. You wait for the server to respond. Once the entire response comes through, you have it all available. The res object, it's typically going to be responded. It'll be curl_OK, which is a constant exported by libcurl. And we'll look at some examples in the demo. Similarly, we can use post. We set the method to HTTP post. In this case, we can make a request body. So in this case, I'm sending JSON to the Postman. If you've not used Postman before, it's a publicly available web service that you essentially send it a JSON request or an API call, and it responds with exactly the same thing back. So it's an echo service. We tell it the content type is application JSON using the HTTP headers. And then again, we call curl execute. And this time we pass in curl, we pass in the request body and the headers. And then we set a callback function. So in this case, do D. And D should receive, so D is a function, D is the data in this case. It should be an array of uint8 or a vector of uint8. Sometimes it is not, and that has to do with how libcurl works. But I'd say in almost every case I've tried it, it has been an array of uint8. And we just attach it to a data buffer. In this case, the data buffer is a uint8 vector that we created. And so again, you can get your response body by converting that to a string. If you wanted, you can be a little more complicated in here. So like in our application, what we would do is we would start parsing the data as soon as it comes in. So as soon as data comes in, we look for the start of a JSON object, and then we keep looking till we find the end of the data JSON object, and then send it off to another thread to be processed while this thread continues receiving data over the network. And you can do that in parallel with multiple threads processing data and downloading data at the same time. So that makes this pretty efficient to, you're not waiting for one job to finish before you start the next job. So how would we do mutual TLS? I mentioned HTTP.jl, it's kind of complicated. You have to create an SSL context and then pass it a lot of parameters. In CurlHTTP, this is all you have to do. You give it the path to the certificate file and the key file, and optionally the CA certificate, the certificate authority file. And that's all. If you've done that, it will essentially use mutual TLS. By default, it will always use TLS if necessary. So if your URL starts with HTTPS, it will use TLS. You don't have to configure it or anything. If you wanted to use mutual TLS, that means your own client certificate, you would pass it these paths, and that's all you have to do. Creating those certificates is out of the scope of this talk, but essentially the OpenSSL command will let you do that. You can also make all of these into one single file, right? So essentially you take these three files, concatenate into one, you put the certificate and certificate chain first, then you put the private key, and then you put the CA certificate, all in one file. We have done things like this, for example, in our CI system where we can only upload one file. Actually, we don't upload, we mount a secure file into a Docker container. So we can do this such that the file itself is not distributed, it's still secret, but our tests can run by using a secret file. And by default, it'll validate all certificates. You can turn that off using configuration parameters. I'll say that this file, when you combine, you can also have junk in it. So for example, we have appended it to the bottom of our ODBC INI file, and CurlHTTP will just ignore everything else. It'll just look for the certificates in that file and use those files. It does print out warning messages, but you can disable logging when you're doing that, and it's fine. Yeah, you don't need to do anything special if you just want TLS. The default is to use TLS if available and necessary. By default, it'll use the most secure options available, so we constantly keep track of which versions of TLS, SSL, or different libraries are currently supported and currently considered secure or insecure. There are very often vulnerabilities found in different versions of SSL, like SSL 1.3 or 1.2 or something. So we will disable those versions as soon as we find a vulnerability. So the default options we use always follow so redirects, 301s, 302s, 303s, etc. Verify the peer, which means verify that the peer that's the other end, either the server or the client, does have a valid certificate. Verify host is verify that the certificate matches the host name. So you might see this very often if you try to connect over HTTPS to an IP address or a CNAME that's different from the common name. You'll get an error in the browser saying that the host is pretending to be something else. That's because it's verifying the host and saying that the certificate and the host name don't match. The SSL version, we use the highest possible that's secure. That's 1.3. It's called SSL version, SSL verify host, and all that's all legacy. In the past, before TLS, it used to be SSL, which was application level. So the encryption has moved down to the transport layer, but people still call it SSL. It stands for Secure Sockets Layer. HTTP version, we will try and pick whichever is the highest version the server supports, up to H2. Do not currently support H3. Once the version of libcurl shipped with Julia supports that, or I'd say we're working with Julia 1.6 here, so libcurl is as standard lib, so we can't upgrade that separately, but in newer versions of Julia, you can upgrade libcurl separately. So we would be able to use H3 at that point. TCP fast open is disabled because there is a vulnerability in that. Typically, what fast open does is if you've already connected to a server before, it'll just reopen that TCP connection without trying the full handshake. But some servers can use that to detect if you are using multiple websites that are hosted on the same server. So it's disabled by default. TCP keep alive is on. Accept encoding is the type of compression used. So whether you can use gzip compression over the wire or bzip2 or Brotli or anything else, we will use the best available that the server can support. Transfer encoding is also for compression, but it compresses the entire request, so not just the body, but also the headers and all of that. And DNS cache timeout is disabled, so by default, curl has its DNS cache on its own and has its own timeout. We just disable the DNS cache because your DNS server should be doing the caching and not your application. So how do we do parallel requests? Again, not too hard. Like I said, you have curl easy, so you would create multiple curl easy objects, and then you would add them to a single curl multi object. So in this case, right at the bottom, we have multi is equal to curl multi, and the pool, which is an array of curl easy objects, and then you call curl execute on that. If you can have different callbacks for each of the requests. So when curl execute is called, all those requests go out in parallel. They come back, the responses come back asynchronously in parallel. The callbacks are called asynchronously, and they will run all in the same thread. So you don't have to have multiple threads or multiple memory spaces for that. It'll all happen in the same place, and you can process them as required. So the requests are only made when we call curl execute. You can keep adding curl easy objects to it, but nothing happens until you call curl execute on the multi object. And responses are streamed back in parallel. So this is a way to stream it. Like I mentioned, your callback here. You can keep reading the data out of curl user data. And I'll show you an example of this now. So let's see if I can switch to this. I think I have to exit full screen first. All right. This is going to be fun because I can't see what I'm typing. Yeah, just give me a second. How's that? Is that readable? All right. So, readable to the people at the back? All right. Let's go into shell mode. So rather than typing everything, I wrote the code down as a as a file, which I will just execute. So I'm using CurlHTTP JSON 3. Don't worry about that no body. It's just a constant, so that I know I don't have any body. And then we're appending everything to a data buffer, which we're going to read. So this is again calling the postman echo. And we read it, we parse the JSON, and then we call curl cleanup. Okay, that's one thing you need to do at the end of the your code you run, curl cleanup. You don't strictly have to do this, so we have a finalizer for the curl easy object. And so when that goes out of scope, curl cleanup will be called, and all the memory and resources will be freed up automatically. But I've just put it here for completeness, so we can see the example. So. Shell mode is enabled, you're right. Did I type that right? Okay. So, did anything happen? Double. Yeah. All right. So this should run this and essentially store everything in data. And if I print out data, that's essentially the dictionary of the request that was sent. So what it did was it did all of this, sent the request out, got the response back, parsed it, and this is the response. It's sometimes easier when you turn on verbose mode. So let's do that. Yeah, I just wanted to print out the code. So where I'm calling this. And I know you can't see the, let me just move that out of the way. All right, does that look right? Verbose equals true. All right, so it's created the object, and you can see that's the object. It contains a pointer, that's the actual libcurl object, and a bunch of other things that are stored internally. All right. And what was the second line there? We already have a data buffer. Let's just call the request to curl execute. So that's basically all the request and response information that was printed out there. There's quite a lot of stuff. Essentially, it's finds the IP address, tries to connect to it, connects, does all the TLS things, negotiates. This is the host, so the certificate that it's pulled down, it says this is the common name postman echo. It matches the host name that we connected to, so everything's fine. And then it goes down and makes the actual request, which is further down. So right here, it makes a GET request. These are the HTTP headers that it sends through. You can see that the accept encoding is deflate and gzip. That's a type of compression to use. Transfer encoding also is gzip. Then the response that comes through, and any cookies, and the data. It doesn't actually show the data here because the data might be too large and might go over the screen, but you already have the data. So that was the simple request. The parallel request I'm going to show you is multi-post. So this one's going to make multiple requests. It's pretty much the example I had in the slides. What we're going to do is we're going to print out the responses in different colors so that it's easy to tell which the first, second, and third is. The light red, light green, and light yellow for the three. This is the last slide. that right? Okay. So it makes multiple requests, and you see here, this is one of the responses, which it should say this is handle number 2, which came in third. This is handle number 1, which came in second, and handle number 3, which came in first. So it sent out three requests in parallel, got back the responses at different times, and printed them out whenever it got the response. Right, so that is pretty much it. It's my last slide. It's a summary. There are some enhancements over existing ways of doing HTTP. Mainly mutual TLS and single task parallel requests are easy. We have open issues. If you try to use it, open an issue, try to respond as quickly as possible. Thank you.
Yeah, if we have any questions, we have room for one.
Thank you for the talk and the package. Just one question: is this multi-threaded safe, the client?
Yeah. So LibCURL itself is multi-thread, is thread safe. You can use it. There are some functions so some of the memory locations like error buffers and stuff are not always. So I would say to read the libcurl manual for the features you're using. So most of the documentation here is for CurlHTTP. There'll be more documentation on libcurl, which is the C documentation. So I'd say specifically look for those things, like the error buffer. Is it going to be shared across threads? Because otherwise you'll have one error overwriting the other. In the way we are doing it, it does not happen, right? But there might be other cases, like it typically allocates the error object inside libcurl, and you have to free it outside. So there's some bit of complication there when you have multiple threads.
Oh, so is there a way to pass options so that it becomes thread safe?
Yeah, you can pass options to curl through CurlHTTP. So there's the curl set opt method that you can pass in.
Okay, thank you.
Yeah, thank you, our speaker, for this great talk. It's always a pleasure to see when Julia moving into this mature language with a good web interfaces already. So great round of applause for the speaker, because we have a real life code there, man.
Thank you.